Yo, what's up, guys? Welcome back. I think episode 89 today. Fuck, man, it's crazy that we're already at episode 89. I think so. Maybe it's 90. No, it's 89. Okay. We'll look at a muck today. Let's take a look at the sound. Muck, Pokemon sound. We'll take a look at this one. I don't know how the hell I meant to mimic that. That's my attempt at a sound right there. But yeah. Yeah, man, it's crazy. 89 today. 89, and we got a lot more ahead of us. So, probably at least another 100 episodes, maybe 150. So, yeah, we're going to keep grinding. So, let's take a look at the problem of the day. I got to sign back into Leetcode. Log me out, bro. Looks like we got an easy problem today. Let's take a look. Minimum number of operations to make elements in an array distinct. The first operation is the first three elements are removed, resulting in array 4, 2, 3, 3, 5, 7. And second operation, the next three elements are removed, resulting in array 3, 5, 7, which has distinct elements. I don't know why they would remove. Given an integer array nums, you need to ensure that the elements in the array are distinct. To achieve this, you can perform the following operation any number of times. Remove 3 elements from the beginning of the array. If the array has fewer than 3 elements, remove all the remaining elements. Note that an empty array is considered to have distinct elements. Return the minimum number of operations needed to make the elements in the array distinct. Okay. Don't think this should be too bad. How to use a queue to pop first element in Python. Is there a special method, maybe? I don't know. Pop left. No. Okay. There must be no method. Okay. At least we know that it's always the first 3, right? So what am I thinking? What's the best way to do this? Suppose we have to figure out if it's distinct, right? So that means every single element is unique, right? So we need to check if it's unique, right? The way we want to do that is let's create like a helper function. Let's call it check distinct, right? Distinct, where we pass in our array, right? Okay. Inside of here, we can do, well, how do we check if it's distinct, right? We have a hash set, right? So let's create our hashy. Hashy is equal to set, right? We loop through, right? So for I in array, if I in hashy, we instantly return false, right? And if not, we instantly return false. Otherwise, we just want to add to our hashy, right? So we do hashy dot add, and we just add I, right? If we get through this, we will just return true, right? So a simple little helper function, right? And then we would simply check, well, while, I don't know if we can do this. I've never really thought about this. We can check, well, while check distinct array check distinct array is equal to false, right? Then we can loop through this, right? Or we just remove the first values, right? So we would just do, well, let's like make our own array here. Let's do res is equal to nums, right? Okay. We do, well, while check distinct res is equal to false, then we can simply remove our first three values, right? So we would go, well, like res 0 dot remove, right? Res 1 dot remove, res 2 dot remove. Actually, we have to think about if the array has fewer than 3 elements, then we remove all remaining elements. Okay, we have to count the operations too, right? So every time this function is called, this check distinct, we need to increment our count by 1, right? We need to initialize our count over here. So let's do count is equal to 0, right? Let's think about here, well, check distinct res is equal to false. We need to think, well, how can we move these values up to where we're at? All right, so we check, well, if res.length is greater than or equal to 3, let's actually take the length every time. So let's take the length is equal to res.length, right? If the length is greater than 3, then there's probably a way easier way to do this, bro. Like, I'm just kind of thinking about on the spot. We take our res, right? Check, well, if our length's greater than 3, then for I in range 3, we just remove the first value every time, right? Else, we go, well, for I in range length, we just remove every value, right? Otherwise, we just return res. Oh, we return count, sorry. Cannot access local variable count where it's not associated with a value. Okay, we need to pass that in. Shit, we're not even calling our function. Oh no, we are. Now I'm gonna find like a super fast solution, and it's gonna be like, bro, like. I want to figure out what the best way is to figure this out. Is it passing in, or can we just make it non-local? Like. Which is declared outside of that function. Python treats variables assigned in a function as local to that function unless you explicitly declare them as non-local or global. Oh god, yeah, I'm thinking about length res. So apparently the best way is to declare this as non-local. Valid syntax, non-local. Non-local count. Then we do, sorry, count plus equal to 1. It has no attribute remove. Oh, okay, right. Well, we can just res is equal to, I forgot we can slice in Python too. We can do this, right? Or otherwise we can just remove all the values, right? And make res is equal to this. Expected 0, 1. Well, this is unique, right? So maybe we can do, well, if set nums is equal to nums, we just turn 0. I think we can fix this easily by going, no. Length set nums is equal to the length of nums. We just return 0. Okay. How do we get 2 here? My logic's off. mic's messed up. I'm gonna fix the mic really quick. Okay. Our logic's off here, right? So we're passing in 5.5, right? So this goes into here, checks, and then it checks again. So we messed up that logic, right? So we need to what do they say? Your removal logic can be simplified if like. It's because I'm entering this loop twice, right? Because I'm looping through this while. I'm checking if it's false, right? So originally it's false, okay, right? Because we have 5.5. We loop through here. We change it. We remove all the values. And then we go into it and we check again. And that's when we increment again, right? We get 2. But we shouldn't want to increment again. So maybe we need some sort of like if statement down here that checks. Let's do like if how can we compare this? So that res is equal to the length of res. Then we can just break out of this loop and return the count. Got something messed up with my logic, dude. Okay, I'm gonna restart here. My logic's kind of just all over the place. Okay, I'm gonna return. I'm gonna get rid of this, right? Obviously, we can do this to deal with the initial. Right, we make our count. Okay, well. Let's do while length nums does not equal length set nums. Okay. We can simply increment every time we do this, right? And we can if the length of nums does not equal is greater than or equal to 3, then we just want to res is equal to res. We go from 3 to the length, right? Else, we just want to make res equal to 0, right? Our res equal to this, right? Let's try that, and then we just return our count, sorry. Cannot access local variable res. Oh, sorry. This needs to be nums. Okay. I just over-engineered that like way too hard. Like, okay. Yeah, nice. Okay, let's take a look at some graph problems. We want our, I don't know why this didn't load, right? We want mediums and we want tag of graphs, please. Graph. Sorted by acceptance. Let's take a look at find champion too, bro. The Ren team's number from 0 to n-1 on a tournament. Each team is also a node in DAG. You are given the integer n and its 0 index 2D array edges of length m representing the DAG. What is a DAG? A directed acyclic graph? I think that's what it is. DAG graph theory. A directed acyclic graph is directed graph with no directed cycles. Isn't acyclic graph? Isn't that with a? Is that a graph that contains no cycles? Okay. What's the opposite? Is it like? I thought a cyclic graph is a graph that contains at least one cycle. I thought acyclic was no cycle. Oh, that contains no cycles. Okay, I was reading it wrong and I'm tripping. Okay. Indicates that there is an edge directed from team U to team V, right? A directed edge from A, B in the graph means that a team A is stronger than team B, and team B is weaker than team A. A directed edge from A to B in the graph means that team A is stronger than team B. Team B is weaker than team A. Team A would be the champion of the tournament if there is no team B that is stronger than team A. Return the team that would be the champion of the tournament. If there is a unique champion, otherwise return -1. What is... What is find champion 1? Find champion 1. Is that a graph too, or... Oh, matrix. Huh? Maybe we can take a look at that one later. Okay. Anyway. Team 1 is weaker than Team 0. Team 2 is weaker than Team 1, so the champion is Team 0. So here we have to think about the in degrees, I think, right? So Team 0 points to Team 1, Team 1 points to Team 2. Team 1 is weaker than Team 0. Team 2 is weaker than Team 1, so the champion is Team 0. So there's not a clear winner here. Is that why it returns -1? If there is a unique champion, otherwise return -1. Okay. So we have to think about the in degrees here, right? Because obviously the team with 0 ins is going to be the champion. Okay, well, let's do our basic first, right? Where we simply create our adjacency list, right? We pass in our graph. We want to do, okay, I'm going to do for I in graph, right? Sorry, let's put edges. We initialize our graph, right? Oh, right, initialize our graph. For I in graph. What we could do, well, for edge and edges, sorry. Right, we just want to take, well, AB is equal to edge. Then we want to check, okay. Well, for I in no, we want to do, okay, if A not in graph, then graph A is equal to this. And we simply just do, well, graph A dot append, we just append B, right? Let's call it adjacency list. Sorry, graph is equal to AJ list. Passing out our edges, right? And let's print our graph. Oh, we're not returning anything. We want to return our graph. Zero, 1, 1, 2. Okay. 0, 1, 1, 2. Right, so we got all our edges done properly. We have 0, 2, and then 1, 3, 1, 2, right? So now really we need to check, okay, well, I don't even think we have to do really any theory here. We can just simply in degree, right? Okay, we would loop over this for I in well, actually, let's just take the length of the edges, right? So we do, well, length, let's do length is equal to the length of the edges, right? Because we will return 2 edges here, but we have 3 nodes. Because there's no cycle. Maybe we can just do length of the edges plus 1. Let's do vertices. Alright, we'll do for I in for vertice in range vertices. Okay. we can check, well, graph vertice. We can do, well, in degree vertice is equal to ADJ list vertice plus is equal to the length of ADJ list vertice, right? But we only really need to do equal because we're not going to go over it again, right? Right, well, if it's the length, we're going to get 1 here, right, with 0, and we're going to get 1 here for this one. Right, and then the other one, really we have 2 would be 0, and we would return, well, with 0, 0, 1 in here, then we return that. That's kind of like my thinking here. So for vertice and range vertices, let's do, I think we're going to need a default dic. How to import default dictionary, Python. Okay, let's import this. Right. How do we initialize the default dic? In degree. Function is not subscriptable. I think it's, we're not getting it is because we're looping through and it's not existing in it. I think that's the reason. Times graph, but then you're trying to do ADJ, that won't work because ADJ list is not the function, not the ADJ list is the function, not the dictionary, even if you assign. I think I can figure this out, right? I think because we're looping through here and we have edge and edges, AB is equal to edge. If A not in graph, graph A is equal to this, right? But we don't actually get to like a 2, right? So maybe we can simply just do, well, if B not in graph, right, we can just simply initialize it, right? Just so it's in there, right? Okay. Are we printing our graph, then? Oh shit, we're not printing. Are we even calling it, then? Okay, graph is equal to ADJ list graph edges. Let's print our graph. Let's see what this gives us. Okay, so now we're actually getting an empty array, right? Okay, so now if we have the in degree, do well for now instead of calling this, we can just loop through all our edges, right? We can do well for I for node in graph, right? We can check well. Okay, we can do, okay, in degree node is equal to the length of graph. Sorry, yeah, graph node. Okay, let's now print it. Let's do print in degree. That worked. Okay. So now we have to do, well, okay, we return. Okay, so now we have to figure out, okay, converts to in degrees. Okay, so now we have to figure out, okay, how can we loop through this? So let's do, okay, in degree is equal to dict in degree. Alright, converts from default dict to dictionary. Then we check, okay, we go, well, for node in, let's do for key value in -code dict dot values, right? candidates is equal to, we have to do list comprehension here. Let's try this on our own. List comprehension. Python. Gosh, man, these websites make it so difficult. Just show me the syntax, bro. Okay. Candidates. The fuck? Okay. We will do, okay, so X for X in degree. If graph X is equal to 0. Let's print our candidates here. Candidates. X for X. Guess we can do it for in range N if graph X is equal to 0. I think that should work. Maybe we can do this. Block this. Let's print out in degree. Print out in degree. Two is 0. Oh. I think we did this one wrong. Why is that? We're counting wrong. We're counting wrong for it because we need to count that the ones that don't have any edges coming into it. So I think we did this wrong. Let's get rid of this, right? Let's print our. Oh, jeez. Let's print our in degree. Oh, whoops. Let's get rid of this. What is the outgoing edge here? 0, 1, 1, 2, 0. So instead of printing the keys, right, we want to put the value, right? So we would put, okay, well, node 1 has an outgoing edge of 1, right? So we would do, okay, in degree node. So we're looking at node 0 right now. We check, well, okay, node 0. Okay, so they have here, well, for U in graph, they have for V in graph U. Okay, so what are we doing here? We're checking, well, for U in graph, so here, and then for V in graph U, 1 degree node is equal to so they have, okay, for U in graph, right, so we go to the node, we check, well, for V in graph U, right, which is this one, in degree V, 1 plus or equal to 1. Okay, that's where we messed up. Okay, then we print our in degree, then we can simply get our candidates, right? 1 1 2 1, right? Two's got nothing. Okay, let's print out candidates. Candidate still gets 2. And we get nothing. 1 1 2 1, right? 1 1 1 has on one incoming edge, 2 has one incoming edge. But now how do we add the 0 though? Bro, I'm kind of stuck now, dude. For x in range n if graph x is equal to 0. How can we make this 0? we can do an extra 4 here and just do like, well, for add extra zeros, right? We could do like for I in length n, if in degree I if I not in degree, then we do in degree I is just equal to 0. Let's print out in degree. Range n. Okay, maybe that will work. Let's print our candidates. Bro. How are our candidates 0, dude? What the fuck? Dude. What is going on here, bro? We have to make in degree is equal to dict in degree. Do we have to make it a normal like dictionary or something? No. I don't know. Why is candidates not printing the 0? You're checking if graph x is equal to 0, but graph x is a list of neighbors from your adjacency list, not... Oh my gosh, I'm checking graph in degree, bro. Oh my gosh, bro. There we go. Okay. Now we return candidates 0 if the length of candidates is equal to 1, else -1. I believe this should run now. Okay. Jeez, man. Oh my gosh. It's the slowest solution, bro. Let's go, dude. Let's go. What do they do here? They do outgoing edges default dict, incoming edges default dict, count the edges. Yeah, they do a similar way. Mine was a little bit overkill, but hey, I got it to work, so. Dude. A likely follow-up question might involve topological sorting. Okay. What is this, bro? Travel back in time. Finish one missing challenge. The fuck? Tickets may make a... You can use your ticket to make up any invalid or late submission for all problems. You're eligible for rewards according to the updated submissions. Oh, I got 667 points, dude. Let's go, dude. Oh my gosh. A daily coding challenge. I can time travel back. Oh, okay, okay. Damn, bro. I want to get a big notebook, bro. Nah, dude, t-shirt. Nah, man. I want to get a hat, bro. Low key, like, that'd be fire. Go to a mission, 30-day streak checking, complete daily challenges, contribute a test case, contribute a question. Contribute a question? Oh, that's cool. Okay. 30-day limit JS basics with 30 questions. I kind of want to do this, dude, low key. I think I'll do that at one point. How long are we going for? About an hour? Let's do another graph problem. Course schedule 2. Apparently easier than course schedule 1. I guess we can take a look. Let's take a look at both though. Course schedule 1, what do we do here? You're given an array prerequisites I indicates you must take course B1. Okay. The total number of num courses you have to take labeled from 0 to num course -1. You're given any prerequisites where prerequisites I indicates A1, B1 in case you must take course B1 first if you want to take course A1. For example, the pad 01 indicates that to take course 0, you have to first take course 1. Return the ordering of courses you should take to finish all courses. If there are many valid answers, return any of them. If it's possible to finish all the courses, return. If it's impossible to finish all the courses, return an empty array. I kind of wish they kind of provide you with a picture of the graph. I kind of like that, to be honest, but there are a total of 2 courses to take. To take course 1, you should finish course 0. So the correct course order would be 0, 1. Okay. Okay. This is definitely a tough problem, right? Because you have to think about cycles. You have to think about ordering of this. You have to think about, like, I don't know. It's very tough. Definitely a tough problem. Let's kind of think about this, right? So let's draw kind of our vertices here, right? So we have 0, just to kind of visualize this problem. 0, we have 1, we have 2, right? And we have 3, okay? So we have 1 into 0, right? We have 2 into 0. We have 3 into 1. And we have 3 into 2. Do we have a cycle here? I don't think we do, right? But in this case here, let's actually, bro, let's move this 3 over here to down here. Alright, so we have 1 into 0, 2 into 0, 3 into 1, and then 3 into 2. Right, so I guess cause 3 is the what we return first, right? Okay, never mind. I was totally wrong. Cause 0 is what we take first, right? Then we would return, well, course 2, course 1. Then total focus say take course 3. You should finish both course 1 and course 2. You should. But courses 1 and 2 should be taken after you finish course 0. Okay, so it goes kind of this way, right? So what can we notice here in this graph? Right? We can notice I think we have to order it by probably the in degree, right? That's kind of what I'm getting here. We order it by the in degree, right? Because this in degree here would be 2. This in degree here would be 1. This in degree here would be 1. And this would be 0. So I'm thinking we would get a hash map and somehow order it by our in degree. That's kind of what I'm thinking here is the move. Why would this return 0? We have 1 course, no prerequisites. I don't know. Anyway, we'll get back to that later. Let's do kind of like the main algorithm now. I need to think about, well, could there be cycles? Are we guaranteed that there's no cycles? All pairs are distinct. A1 does not equal B1. It doesn't say specifically that. Let's check. Can this problem have cycles? Can absolutely have cycles. Detecting those cycles is essential. Okay. Okay, so we do have cycles. Well, I'm thinking here. Well, my first kind of thought here as we were doing this is like, do we need to do this? Can we just sort it by the in degree? So apparently we can't, it won't tell you if there's a cycle unless you try to process the node. topo sort. But then you can do this with DFS too. Let's create our adjacency list. We pass it our prerequisites. Alright. Create our graph. This is a directed graph, I believe. Right. Okay. Let's just call this edges, just because why not? Makes it shorter. In edges, we can do, well, AB is equal to the edge, right? If A not in graph, and graph A is equal to this. Well, we can simply check here. Well, we gotta return our graph too. ADJ, let's do graph is equal to ADJ list graph. Let's print out graph. Oh, whoops, this needs to be prerequisites. Let's check out course schedule 1. What are we doing here? We're building the graph. Turning the graph. So we're just building our adjacency list, right? But we're simply, I guess, if B not in graph, graph B is equal to this. Alright, which gives us this here. Yeah. Okay, let's do, well, now pretty much we need to call our DFS function, right? So refreshing water, bro. Okay. But what do we need to return here? We need to return We're gonna have to create a res array, right? Because obviously we're gonna have to return our res. Okay. And then we're gonna have to somehow call our DFS function, right? So we have to do, well, DFS, right? We're gonna have to pass in our graph, our starting node, we're gonna need a starting node. How are we gonna do the visited? How do we do it over here? We created the visited set outside here. Visited is equal to set. Alright, we called out DFS on our graph. And what else did we pass in? And we could just call DFSI. Courses. We called DFSI. Starting from 1, right? This is a lot harder to think about, dude. Definitely not a medium task without trivial solutions. But would consider it easy. I love these comments, bro. They're so funny. Like, I think in 2019 this would be hard, but we consider it easy now. Easy to medium if you know topological sort slash BFS. Otherwise, it is a hard. Don't know how to do it with DFS though. It's a pretty straightforward topological sort. If you don't. Yeah, man, I'm going to need a hint. I'm not sure kind of how to solve this with DFS. And I don't really know topological sort. Sorting is a great way to sort course schedule too. The core idea: visit each course's prerequisites before adding the course to your result list. Okay, I think I understand. So if we want to make our DFS function here, fdfs, we pass in our node, right? What would be our base case as well? We're gonna loop through our neighbors, right? For neighbor in graph node, right? We're gonna check, well, if not in visited, then we're gonna add this node, right? We're gonna add, well, visited.add neighbor, and then visited.append res. When we need a current path, because we're gonna revisit stuff too. I believe that's why we have the path. Oh shit, man. Man, this mic is pissing me off, dude. Oh my gosh, man. Makes so many noises, dude. I have to unplug it again. Okay. We start at 0, right? So we start at 0. And we check this node's prereqs, right? We go for iron range num courses, right? So we would start at 0, right? So this 0 doesn't have any outgoing edges, right? Zero has no outgoing edges. We wouldn't do anything. We would just call. Really, all we want to do is we want to see that it's visited, right? called DFS neighbor. So we loop through the nodes, right? We check, well, for neighbor and graph node, we don't append anything to it, right? Apparently we need a has cycle is equal to false, right? Okay, non-local has cycle, right? We do for neighbor in this, we DFS neighbor, right? If it doesn't have any neighbors, path up remove node. Doesn't have any neighbors. We're gonna path up remove node. We're gonna add it to visited. And then we're gonna append it to res. Because it doesn't have any neighbors, right? Because if there was neighbors, then we know we need to take that course before we can take our own, right? That's why we're appending, we're adding and removing down here, right? What would be our base cases though? If I guess, well, if node in visited, I guess we just want to return, right? We also want to check, well, I guess if node in path, right? Because if it's in the path, we have found a cycle. So we would do return, right? We check, well, if I not in visited, then we can do this, right? Has cycle. We return empty list. Then we would return the reverse. I'm running off the deep end, sick of playing defense. didn't really work, dude. What is... Return false. I'm not sure what's wrong with this, bro. Like, I don't get... Bro, this is so hard, bro. Okay, screw this. I'm just gonna return this to see if this works, because I'm curious. Probably will. It's gonna make me sad, but bro. For edge and edges, do this, right? Am I like just doing this wrong, bro? Like jeez, bro. Like, I need to print this, bro. AJ list graph. I'm actually so hungry too, bro. Like, okay, let's do graph. Let's print our graph. I want to see what this gives us, bro. Res is not defined, bro. Oh my gosh. 1-0. So, what are we looking at here? Well, this is incorrect, bro. So we have okay, so we've got, it's something wrong with our adjacency list. But why? What are we doing wrong here? What is wrong with our adjacency list here? There are a total of 2 courses to take. To take course 1, you should have finished course 0. So the correct course order. To take course 1, you should have to finish course 0. Right, so AB. If A, not on graph, right, we're just making it here. We're doing graph A. Dude, what is the difference here, bro? I don't understand what the difference is here. Like what, bro? Like what is the difference between this and this? I don't understand. Like I bet you now it'll run. Yeah, like, bro, what is the difference here? Like, we're going through the graph. For every I in range num courses, we're making an empty array, right? So 0, 1, and 2, we're making an empty, 0 and 1, right? For A, B, and edges, we're appending B to A. So we're mapping 0 to 1. So to take course 0, you need to take course 1, right? What are we doing here? The same thing, bro. To take mapping 0 to 1. Like, what? Okay. I for I in range num courses. I for I in range num courses. For I in range num courses. Now it's gonna freaking submit, dude. Oh. Okay, so what are we doing here, right? So we're creating our graph, creating our res array. We're looping through, right? So we start off. Take a look here, right? We start off for I. We start at 0, right? We loop through. If node and visited, well, it's not. If node and path, well, we don't have a cycle either, right? We add to path, right? So we add 0 to path, and then we add its neighbors, right? For neighbor and graph node, right? Well, DFS doesn't have any neighbors, right? Actually, let's print this just to be sure. Let's print our graph. We print our graph, so we have. Well, actually, we're mapping it the other way now that I think about it. So it does, right? It would have some moves. So for neighbor and graph node, right? DFS neighbor. We call DFS on our neighbor, right? So now we go through and we have, well, if node and visited, well, it's not, right? If node and path, well, it's not. We're at a different node. For neighbor and graph node, right? So now we're at 1, right? We call DFS neighbor. Well, there's nothing in graph node, right? So we go through here and we do, well, path.remove node, right? We'd remove the node, we'd add it to visited, and we append the node, right? Which means we'd come back to our original call and do the same thing. We'd remove, we'd add to visited, and then we'd append the node, right? And we'd append the node, right? So we'd go back to 0 and we'd append the node. Oh shit, we don't want to print res here. We want to print it after this. Well, we'd append node 1 first, right? How are we appending node 0 first? Oh no, yeah, we would append node 1 first, right? Because we go to 1, right? We go from 0 to 1. We finish that DFS call, then we append 1. We return back to this one. And then we check. Then we move path visitor.add and we append our 0, right? So then we have 1, 0, and then we have to flip it around, right? If node in visited. We found a cycle. So we have an in progress here to check our actual current stack, right, which is our path in this case. We have a complete visited, so we know we visited that node, and then we have a res. It is an interesting problem for sure. All right, guys. I think I'm gonna call it there. That problem was a little bit of a crazy problem. We did a few problems today, and I'm happy with that. So, gonna get back to doing some other homework and other things like that. So, appreciate you guys watching. I will see you tomorrow.